Morning, everyone. We'll get started in a couple of minutes, just letting people join. The number of attendees is rapidly shooting up, so we'll give people a couple of moments to get onto the system. Good morning, everyone. Numbers seem to have plateaued or started to slow down, so we'll kick this off this morning. Thank you, everyone, for joining. I'm Robert Kerris, Longevity Lead at Lloyds Banking Group, for those who don't know me. So today's sessional meeting is a value at risk approach to misestimation risk for longevity risk. And it gives me great pleasure to introduce Dr. Stephen Richards, who's the Managing Director of Longevitas, a specialist provider of mortality analysis software for actuaries. And Stephen is an honorary research fellow at Heriot-Watt University, and as many of us on the call will know, has made big contributions to the modelling of longevity risk over the last decade or so. So with that, I'll hand over to Stephen. If anyone has any questions, please post them in the chat, and we'll cover those at the end of the session. So Stephen, over to you.
Thanks, Rob. Welcome everyone to the presentation on the value at risk approach to misestimation risk. The sessional meeting paper is available on the profession's website. If anyone subsequently wants to put in any written questions for the transcript of the discussion, should feel free to do so, and I will try and answer them in due course. This is a follow-up paper to a paper I wrote in 2014, addressing the very specific question of how to look at misestimation risk through a value at risk approach. So the presentation is relatively technical and relatively detailed. I'm not going to assume that people have read all of the paper. I'm going to look at some of the background about misestimation risk. I'll then look at some very specific features of portfolios, specifically annuity portfolios, because I've got lots of data for those. But many of the features apply to a lot of other portfolios actuaries will work with. I'll then do a little recap on parameter estimation, specifically maximum likelihood estimation, because this is very relevant to misestimation risk. I'll look at a number of critical preconditions for the misestimation assessment to produce valid results. I'll then recap what we'll call runoff misestimation, which is a misestimation without a value at risk element. So this is a refresh of the 2014 work. Then I'll contrast this with the value at risk approach to misestimation, look at how we have to modify our algorithm to look at it from a value at risk approach, and then contrast the results and look at some expected and unexpected aspects of the value at risk view. I'll do a number of detailed comparisons so that we can get some insight into how this methodology behaves, and then there'll be conclusions, and there'll be quite a large period for questions. We've got up to maybe 40 minutes for questions at the end. So we'll go back to beginning with misestimation risk and its definition. A good place to start is Sam Wood's definition. He was talking specifically about longevity risk, but a similar comment would apply to other risks. And the PRA considers that longevity risk contains at least two subcomponents, one being the base misestimation risk and the second being future improvement risk. So we'll start with the PRA's view of the world, which is longevity risk should decompose into at least two sub-risks, namely your current mortality rates and future projections. And Burgess and others noted that the risk that your base mortality estimate being incorrect is what your misestimation risk is going to focus on. So it's the current rate of mortality. And a very important subsidiary point that the mortality basis is presumed to be set based on the actual experience of the portfolio in question. If you're not using the actual experience of the portfolio, then you're going to have to include an additional capital allowance for basis risk, which is the risk that the data set that you've used to calibrate your mortality basis is not actually representative of the underlying mortality of your portfolio. So we critically assume that this is work based on the actual experience data of the portfolio. And then Kevin Armstrong posed the question a different way, which was how wrong could our base mortality assumptions be if our recent historical experience just happened to not be representative of the true underlying rates of mortality. Kevin then went on to point out that the misestimation assessment lends itself to statistical analysis if there is sufficient accurate data, of course. And then Stephen Macon in 2008 pointed out the critical actuarial exception here, which is that the impact of this statistical uncertainty has to be quantified financially. So it's not enough to look at it as a statistician. We have to quantify the financial impact of this statistical uncertainty. So this gives us four key aspects of our misestimation risk. It's essentially the uncertainty over current mortality rates. The future projections or the future forecast risk is handled as a separate exercise. We are assessing our misestimation risk using the actual portfolio experience only. We will be modeling it statistically so that we can get standard errors and covariances on the parameter estimates, but we will have to measure it financially. So it's a statistical modeling exercise, but quantified financially. So we'll look at some of the important features of quite a number of portfolios and how this might actually create particular challenges. So we'll look first, we've got two pension schemes that we'll look at here today. The first is a medium-sized pension scheme with around 16,000 lives. We're just looking at pensions in payment, and there are around 6,000 deaths observed over this 6-year period. And what we can do is we can sort the 16,000 lives by pension size, and we can split them into deciles. So we've got 10% of the membership in each one of these deciles, and so it's about 1,600 lives in each decile. But if we sort them by pension size and look at where the liabilities sit, we can see that on a headcount basis, these deciles are equal, but on a pension-weighted view of the world, they are radically unequal. We've got a massive degree of concentration risk. So the people, the 1,600 members with the largest pensions have got about as much more pension basically than the bottom 70%. So we've got a tremendous concentration of risk. And this obviously is of direct interest to actuaries because that's where the financial liability is. So we've got the top decile of pensioners here receiving about 40% of all the pensions, and the next two deciles, 8 and 9, receiving a further 30%. So we've got 80%, 70% concentrated in 30% of lives. So we've got a tremendous concentration of liabilities. And to illustrate the importance of this concentration risk, we'll look at a simple time varying model for the mortality hazard. So this is the mortality hazard mu x y, so it's the force of mortality varying in by age x and time y. We've got a sort of Macomb-like constant here, and then we've got this Gompertz-like structure here with alpha and beta. And we've got this delta parameter to allow for changes in mortality levels and time. And what we do is that we build a model which actually has an individual mortality rate for each particular life I. So what we do for life I, we determine their value of alpha, which is going to be their level of mortality. And it's going to be built up as follows. We've got alpha naught, which is the intercept. This is the base value of alpha common to everybody. And then we build up a series of additional components depending on whether or not a given life has a particular risk factor. So we have these indicator variables Z, which are either 0 or 1, depending on whether or not the life has a risk factor or not. And then we've got these alpha factors, which are the additions or subtractions to the level of mortality, depending on whether or not somebody has that risk factor. So alpha J is the effect of risk factor J. It could be gender, pension size, membership of a postcode group, whether or not they retired early, and so on. And then we have this ZIJ factor, which is basically just a 0-1 indicator, 1 for whenever the person has a particular risk factor, and 0 if they don't. And using this approach, we can actually build up an individual mortality rate for each individual life for any number of risk factors we like. And this is a table showing the results of what happens when we fit this particular survival model to this portfolio. So we've got our alpha naught, which is our intercept, which is shared by everybody. So all 16,000 lives contribute to that. And then we've got our alpha male, which is the effect of being male. And that's driven by the 6,000 lives who are male, with the other 10,000 being female. Of particular interest are the parameters for the effect of being wealthy or very wealthy. So the parameter alpha for the decile, the 10th decile, the largest pension size group, that has a value of -0.3, and that's driven by the just under 1,600 lives who fall into that group. And the interesting thing is that positive values like the alpha male here, that increases mortality, and the negative values here decrease the level of mortality. So the effect of being male will add nearly 0.5 to the base level of mortality on a log scale, whereas being in the top pension decile will actually deduct 0.3. So it won't quite cancel out the effect of being male, but it will go a long way to offsetting it. And these are very large differences in mortality. So we've got the lowest, or if you like, the poorest people have the baseline level of mortality with alpha naught. The people in the 8th and 9th deciles have 20% lower mortality, but the people in the top 10%, they have 30% lower mortality. So they've got a very materially lower mortality rate, which is obviously actuarially relevant because they actually have a completely disproportionate share of all the liabilities. Now, we'll introduce an item here called the coefficient of variation, which is just the standard error of a parameter divided by its estimate. And this is quite useful because it measures the relative uncertainty over a parameter estimate. And we can calculate this for our various parameters here. And we can see that we've actually got, for a number of parameters, like the coefficient of aging and the intercept, we've got a very small coefficient of variation because we've got a very high degree of confidence in that estimate. But of considerable interest here is that the coefficient of variation for the two largest pension deciles is really quite large indeed. And that's of interest because we now have what seems to be a perfect storm for actuarial work. We've seen that the liabilities are highly concentrated. we've seen that the subgroups with the largest liability actually have the lowest mortality. And now we've just seen that not only do they have the lowest mortality, but the parameters describing that low mortality have the highest relative uncertainty as well. So we've got this actuarial triple where our liabilities are concentrated in a small subgroup where we have actually the least confidence or the highest degree of uncertainty over their mortality rates. So let's look a little bit. This is a quick refresher on some aspects of parameter estimation. We'll assume that we've got a statistical model with M parameters. Now, that in my work, I use survival models, but you can use other kinds of models as well. And we assume that we've got a vector of parameters theta, which would correspond essentially to that column in the previous table. And we have some estimate of theta hat, which is known because we've estimated it, but it is to a certain degree uncertain. And this uncertainty over the value of theta hat is our estimation risk. The more data we have, we would expect to have less uncertainty. The less data we have, the more uncertainty there should be over theta hat. And we make a number of assumptions. So we have a function L, which is the log likelihood function, depending on theta and the data. And this is what a log likelihood function looks like in one dimension. So we've just got one single theta parameter here. And usually log likelihoods have this quadratic upside down U shape. We also assume that all first partial derivatives of the log likelihood exist, so that we've got this function L prime, which is the first derivative of the log likelihood with respect, the first partial derivative with respect to each one of the parameter elements. And we use L to look at the gradients of the log likelihood. So on the left here, as the log likelihood is rising, the first derivative is greater than 0. On the right, when it's falling, the first derivative is less than 0. And obviously at the peak, the first derivative is 0. And this would be where we would find our maximum likelihood estimate, where the first derivative is 0. And our third assumption is that we have a Hessian matrix H, which is of all second partial and cross partial derivatives. So it's every second derivative pair for each of the parameter components. And for maximum likelihood estimation, theta hat is the maximum likelihood estimate of theta if the first derivative is 0, and that the Hessian matrix is what's called negative semi-definite, which we won't go into here. But that's the core of the method of maximum likelihood, really. And this is what we would use, for example, in this on-screen example, in one dimension, we would use these aspects to find the maximum value of the likelihood function. There's the maximum likelihood estimate there, minus 0.49. And then we can evaluate the Hessian, which we can then use to get the standard error of the parameter estimate. Now, this is the one-dimensional example on screen, but obviously extends to multiple dimensions. Now, the interesting thing about theta hat is because it's uncertain, it can be viewed as a random variable in itself. And according to the maximum likelihood theorem, theta hat has an approximate multivariate normal distribution with the mean vector of theta hat and with a covariance matrix sigma hat, which is just calculated as the negative inverse of the Hessian. Now, this is a very useful property of maximum likelihood estimates, which we'll make considerable use of later in the presentation. And this multivariate normal assumption, a normal distribution, basically the likelihood for normal distribution has a quadratic form. And here we can see in the one-dimensional case, the solid black line is our actual likelihood function, which happens to be a Poisson likelihood for this example. And the dashed line shows the quadratic approximation that is inherent in this multivariate normal assumption for the distribution of theta hat. And we can see that the quadratic approximation is actually very good, and that in general, the multivariate normal assumption for the distribution of theta hat is actually a very good one over a very reasonable range. And this means that if theta hat has a multivariate normal distribution, all of our estimation risk is summarized in sigma hat, the covariance matrix. In particular, the leading diagonal of theta hat, sorry, the leading diagonal of sigma hat is the variance of the individual components of theta hat, and all the off-diagonal entries have the covariances of the various components of theta hat with each other. So to summarize, estimation risk is about statistical parameter uncertainty, whereas misestimation risk we could view as the financial impact of that parameter uncertainty. And to put it more formally, perhaps, we could say that the estimation risk is the uncertainty over our estimate theta hat, whereas in contrast, misestimation risk is the uncertainty over V of theta hat, where V is basically our liability function. In the examples in this presentation, V is basically just the reserve, the best estimate reserve for the pensions and payment, but it could be any other actuarial liability. But V is our liability function, which depends on our vector theta hat. So some preconditions before we look at some results. Back in 2013, Kevin Armstrong posed the question that you need to be aware of what assumptions that you're making or not making. He gave a number of examples. So for example, independence, the independence assumption of the individual lives in your data set, the problem of duplicate policies, which is the tendency very pronounced in annuity portfolios for people to have multiple annuity policies. And indeed, the wealthier people are, the more likely they are to have multiple policies. And then the question of amounts-based mortality or lives-based mortality. We saw that earlier. Statistical models are inherently lives-based, but as actuaries, we're very attuned to the concentration risk that comes with amounts. So a number of preconditions apply for any misestimation risk assessment. The first is that you need to deduplicate your records. You need to turn a data set of policies into a data set of people by identifying people with multiple benefits and aggregating them. We'll be using a lives-based statistical model in order to get valid statistical estimates with valid covariance matrices. But we can't forget the amounts effect of mortality, both concentration risk and the tendency for the wealthier people to have lower mortality rates. So we have to handle the amounts effect. We can do this either as a categorical factor, as we did earlier with the various pension deciles, or alternatively, we can in fact model continuously varying mortality that varies continuously with the exact pension size. And in particular, it's important to note that any assessment of misestimation capital will lead to an underestimate if you fail to deduplicate the records before the analysis, if you ignore the amounts effect on mortality, and also if you fail to acknowledge any time trend. If there is a time trend, for example, if mortality is improving, then this needs to be included in the model. Otherwise, the misestimation capital will be underestimated. So let's look at what we'll call runoff misestimation before we come to the value at risk approach and contrast the two. So the runoff misestimation could be posed or could be formulated as the question, what is the uncertainty over V, our liability function, caused by the uncertainty over theta hat? And we have two potential approaches to addressing the question of the uncertainty over our reserve. The first is the delta method, which we'll come to in a minute. And the second is the method of my previous paper. So we'll look at the delta method first. So we've said earlier that theta hat is a random variable, and that V, our reserve function, is a function of a random variable. And this means that we can apply the delta method for functions of a random variable as follows. So the variance of our reserve is approximately equal to the transpose of this vector A multiplied by our covariance matrix multiplied by the vector A again. And the vector A is just the first partial derivative of our reserve with respect to the theta hat. So the elements of A has M elements, and each one is the first partial derivative of the reserve with respect to the relevant member of theta. And we can estimate this by, in the case in this presentation, we've used central differences around the reserve to calculate A. Our alternative method from my previous paper is that we want to generate a set S of liability valuations subject to parameter risk. And then we can calculate percentiles of S, for example, the 99.9th percentile, the median, the average, whatever we like. So we've got two different approaches here. The approach from the previous paper, we start with our best estimate parameter vector theta hat. And we've got our estimated covariance matrix. And what we do is that we use the maximum likelihood theorem and we generate alternative parameter vectors theta prime just by sampling from the multivariate normal distribution using Monte Carlo simulation. And what we can do is each time we sample an alternative parameter vector, then we can calculate our liability function and then add it to our set S. So that's a sampling approach to parameter risk here. So to put this in pictorially, for the sampling method, we start off by fitting one model and we estimate theta hat and sigma hat. We then, using the multivariate normal distribution, we sample our theta prime. We value the liabilities with theta prime, add that liability to our set S, and then we repeat this for, say, 10,000 times so that we have a set S of liability valuations subject to parameter uncertainty caused by the sampling procedure from the multivariate normal distribution. So we'll now look at some results for these two methods, and we're going to look at a larger pension scheme this time. There's nearly 45,000 lives. Again, it's pensioners only, and we have nearly 11,000 deaths over this period. And so we fitted a model. The details of the model are in the paper. It's rather rich in the number of factors. And this is a distribution of S. This is our set of valuations placed on the pensions and payment. And we can see here that maybe the best estimate is maybe about 2.03 billion. But there's a fair degree of uncertainty over the estimate of that liability caused by the uncertainty over the parameter estimate. So we've got gender and pension size and early retirement and all sorts of other risk factors in there. And we can see that the uncertainty over some of these parameter estimates has led to this reasonably wide spread of maybe up to £100 million in the reserve estimate. Now, it's very important to note that this is a misestimation assessment. So this is the uncertainty caused, the misestimation risk caused by the uncertainty over current rates of mortality. If we were to put in uncertainty over future improvements, then first of all, the reserve would go up to the right as we included future improvements, and then obviously it would be more spread as there was greater uncertainty over future improvements. But this is just the uncertainty over current mortality rates. And one question of interest to insurers in particular is what would be the relative capital percentage, RCP, required to cover a proportion P of misestimation risk. So we're going, RCP is essentially our uncertainty as a capital value expressed as a percentage of the best estimate reserve, just to keep things neatly scaled. So in Solvency II work, for example, the proportion P might be something like 99.5%. And we can use these two methods for misestimation, runoff misestimation, and they each have different ways of calculating this the relative capital percentage. So under the delta method, we have this function here. So we've got what's basically it's the square root of the variance divided by the reserve. So this is just the coefficient of variation. And then this phi to the -1, that's the relevant percentage point of the normal distribution function. So for example, if you wanted the upper 2.5 percentage point, then you would maybe use 1.96. And as before, this ratio here, that's just the coefficient of variation, but instead of it being the coefficient of variation of a parameter, it's the coefficient of variation of the entire reserve. The same percentage, the relative capital percentage, under the set-based approach, it's just the relevant quantile of the set divided by the reserve estimate, and then we just take away 1, multiply by 100% so that the RCP is basically just a percentage of best estimate reserve as our capital requirement. And this is what the two methods look like, fairly deep into the tail. So I've just picked the quantiles 90% up to 99.5. And we can see that there's actually a very close degree of agreement between the two methods. So there's slightly more capital requirements for 90 to say 98% under the set-based approach. But by and large, it's actually a fairly close approximation, even quite deep into the tail. So even at the 99.5% approach, we've still got reasonably good agreement here. And obviously the capital requirements as a percentage of the reserve increase semi-exponentially here as the quantile increases. So for runoff misestimation, both the delta method and the set-based method agree quite closely for this particular liability, even quite deep into the upper tail. The delta method is quicker, but the set-based approach is actually better if your liability results are skewed. So if your liability results end up being essentially a single peak with symmetric around that peak, then you could use the delta method in all confidence. But if for some reason your liability results are going to be skewed as in response to the misestimation, then the set-based approach would be better for that. Now, what we've just discussed here is a runoff approach. And now what we're going to do is contrast it with a value at risk approach. So the runoff misestimation is essentially asking the question, what's the uncertainty over my reserve caused by the uncertainty over my parameter estimates? In contrast, the value at risk approach is asking a different question. What's the uncertainty over my reserve that could be caused by re-estimating our parameters based on n years of additional data? Now, this is a different question. The value at risk question is essentially about recalibration risk, which is a term I borrowed from Andrew Cairns. And as you can see on screen, that although both are billed as misestimation questions, they are actually asking slightly different questions. So we would expect them to have different answers. Now, some important points to note about the runoff approach is that it has no new experience elements. You take your mortality experience, you estimate your parameters, and then you can estimate the uncertainty over your reserve. But there's no n years new data element to that. So there's no recalibration component to the runoff approach. And that means it's not a plug-in fit for a value at risk application like Solvency II. So we need to make some changes to make it a proper value at risk approach. So we make two changes to the set-based approach. First is obviously that we need to simulate n years of experience, and we also need to refit our model to the combined real data and pseudo data to re-estimate our parameter, which we'll call here theta hat j, and then proceed as before and generate our set of liability values. And this is what the procedure looks like. It's slightly different. So we fit an initial model for theta hat and sigma hat. We then simulate n years of further mortality experience amongst the survivors. We then refit the model to the combined real data and pseudo experience data, and we will re-estimate theta hat j. We'll then use theta hat j to value the liabilities as before. We add it to our set and we repeat it, say 10,000 times. So the S is then a set of liability valuations subject to the recalibration risk from the simulation of n years of new experience. So theta hat j varies according to, or its variation is driven at least in part by the additional n years of experience data, which gives us a true n year valuation approach, or a true n year VAR approach to misestimation risk. And we can just calculate the percentiles of S as we did before. And this is what we get as a result. So the 1 year value at risk approach to the same portfolio produces a much narrower range of liability estimates. And we can see that the peak is roughly at the same point, but in fact, it's a much narrower spread, maybe of about £50 million in total. So our runoff approach looks at parameter risk, if you like, over the entire term of the liabilities. But the 1 year value at risk approach is being driven by this recalibration risk on a 1 year horizon. So they produce different results. We'll look at this in a bit more detail. So what we have is a survival model again for the force of mortality varying in age and time. And we've got the following risk factors in the model. We've got age and gender, as you would expect. We have normal versus early retirement, first life versus surviving spouses, and we've got pension size in there, and obviously a time trend, because it's very important to include a time varying parameter for mortality improvements. And we're interested in, let's say, the 99.5% value at risk capital requirement. So what percentage of our best estimate reserve do we need to cover 99.5% of all 1 year recalibrations? And what we'll do here is our VAR capital requirement is the analog of what we've seen before. So we take the 99.5th percentile of S, and then we divide it by the mean of S. In the paper, I did some work comparing the choice of the denominator here. For this particular portfolio and for annuity work, it doesn't make any difference if you use the V of theta hat or the mean of S or the median of S as the denominator. It produces the same results in each case. And what we do is we'll look at 1,000 simulations of additional experience in each scenario, 1,000 recalibrations of the model. Now, to do the simulation of the new mortality experience, we have two options. We can ignore parameter risk and just use theta hat each time we simulate the experience and recalibrate the model. Or we can include parameter risk by first sampling from the multivariate normal distribution, then simulating the new mortality experience, and then carrying out the recalibration and the liability valuation. So we can actually do the simulation of mortality experience with or without parameter risk. And it makes a difference. So here on screen, we've got our capital requirements as a percentage of the best estimate reserve here by the various value at risk horizons. So if we're simulating 1, 2, up to 5 years of new experience and then recalibrating, we can see here that we start off by needing about 1.3% capital or misestimation capital on a 1-year horizon, and it goes all the way up to just over 2. And that's the result with the parameter risk when we're simulating new lifetimes. If we simulate and recalibrate without parameter risk, we get these capital requirements, which are broadly constant. But what's of particular interest is the 1-year misestimation capital. It's not massively different from using or not using parameter risk. And this means that although we define misestimation risk as being driven by parameter risk for the runoff approach, we can see here that the value at risk approach, most of the 1-year capital requirement is not driven by parameter uncertainty. That would be the difference between the blue circle and the solid red dot. What we can see here is that most of the what's called misestimation capital on a value risk approach is actually being driven by the idiosyncratic risk or the recalibration risk. So actually, what we would think of as being primarily driven by parameter uncertainty is in fact being driven by the recalibration, not parameter uncertainty. So for our misestimation var capital, obviously adding parameter risk will increase the capital requirements. But we've seen here, at least in this example, that most of the 1-year capital requirement is in fact not due to parameter risk at all. And in fact, even out at a 5-year horizon, only about half of the 5-year misestimation capital is actually being driven by parameter uncertainty. Now, what this means is that the solvency approach, or n equals 1, is actually a rather qualitatively different beast from the sorts of horizons that you use for, say, an ORSA assessment. And the fact that most of the 1-year capital requirement is not being driven by parameter risk, it's being driven by the recalibration, leads us to ask the question, how correlated is our so-called value risk misestimation capital with the idiosyncratic risk in the portfolio? Now, most insurers would hold more than 2 capital elements for longevity risk. They would usually have an adverse deviation risk or an adverse experience risk, which would be another name for idiosyncratic risk. So how correlated is the misestimation capital with the idiosyncratic risk? So what I did here in the paper is I looked at 3 different possible metrics that you might use to describe the idiosyncratic risk in the simulated experience. So we look at the correlation for each VAR horizon of the time lived by the survivors over that 1 to 5 years, or the deaths in the 1 to 5 years in the new experience, or the annuity payments made to the survivors over that year. And we can see here, regardless of which metric we pick, there's actually a very high degree of correlation between the misestimation value at risk capital and the idiosyncratic risk. So if you have a capital matrix that has an element for misestimation capital and an element for adverse experience, then you're going to have a fairly high correlation in your aggregation matrix, because as we can see here, regardless of which way you look at it, these 2 capital requirements are quite strongly correlated. So our value at risk misestimation capital is very strongly correlated with the idiosyncratic risk over the horizon, the 1 year horizon. And that means that we have to reflect this correlation in the aggregation matrix we use for Solvency II. So let's look at the impact of one or two other features. So if we look at the role of discount rate, so we can calculate the misestimation capital, and we can do this with different discount rates. And as the discount rate goes up, the capital requirements come down. So a low discount rate means a higher rate of, higher misestimation capital as a rule. Now, one other interesting aspect would be the choice of mortality law that we used. Now, in the previous slides, I've actually used a simple Gompertz model or a Perks model. And these are there's various mortality models here. So the Gompertz model is the oldest and simplest. The Perks is a variant. It's got the same number of parameters, and it's largely linear on a log scale between ages, say, 60 and 90, but it has a late life mortality deceleration. The Beard model is similar with a bit more flexibility, or we could add a Macomb term to allow for the fact that mortality is not linear between ages, say, 50 and 60. So we've got a wide choice of models here. And we also have a relatively recent addition to the pantheon, which is the Hermit Spline model, which I'll make a brief detour and describe that short now. So the Hermit Spline model is designed specifically for post-retirement mortality. And it's different because it allows for the automatic convergence of mortality rates with age. So if you had a differential, say, for pension size, it would start off large age 60 and narrow to the point where it might be largely gone by age 95. And we use Hermit splines to give us both smoothness and this flexibility. So this is what Hermit splines look like. This is a basis of the 4 Hermit splines. The most important ones are H0 or H00, which is the solid blue line, and then H10, which is the dotted line here. And what we do to turn this into a mortality model is we define X0 and X1 as our minimum and maximum ages. We scale them to define T, which is basically mapping the age range onto the interval 0, 1. And then our force of mortality by age, or the log of our force of mortality, is just a linear combination of these Hermit splines. And in fact, we can very often get away with just using these 2 splines here. So alpha is the level of mortality, and omega is the limiting rate of mortality. And as before, we can vary this alpha value with different risk factors. But in contrast to the other models, the impact of this will decrease with age because of the shape of the H00 spline. And we can estimate these parameters from the data as we do with the other models. And as I mentioned before, the key difference here is that the impact of alpha reduces with age automatically. So we have automatic convergence for the various risk factors. So it means we don't need the age interactions. So it would be the interactions with the beta terms for the other models. And as a result, the Hermit spline model needs fewer parameters. So some questions: which models fit best? And does having fewer parameters in the model mean less misestimation risk? So we've got 2 ways of looking at model fit. So there's the statistician's way, which would be a lives-based approach, say using an information criterion like the AIC. But as actuaries, we know the importance of amounts-weighted mortality. So we also need to look at, for example, a pension-weighted resampling approach, like the bootstrapping procedure described by Angus MacDonald and others. So we've got these 2 ways of measuring model fit as actuaries. And then there's also the question, what counts as the best fit? Well, by lives, the best fit is usually the model with the lowest information criterion. And for our amounts criterion, basically having a bootstrap percentage as close as possible to 100%. So here we have our 5 models sorted by descending AIC, so worst fit at the top, best fit at the bottom. And we can see here the number of parameters in these models. So that the Hermit model has the fewest parameters because it doesn't need these age interactions. The other models need age interactions to have mortality differentials narrowing with age. In terms of the information criterion, the Gompertz model is by far the poorest fit. The Hermit model is the best. The Macon-Perks is a close second. And then in terms of the bootstrapping percentage, the Gompertz one is probably the furthest away from 100%, and the Perks and the Hermit models are the closest to 100%. Not perfect 100%, but obviously the closest. So we can see that the Gompertz model has the worst fit in terms of both lives and amounts. And in contrast, the Hermit model has the fewest parameters, has the best fit in terms of the information criterion, and the second best fit in terms of explaining amounts-based variation. And then the natural question is, does this carry forward into the misestimation capital requirements? So these are the capital requirements by various horizons using the different models. And we can see that the Gompertz and Hermit models, having the fewest parameters, actually have some of the lowest capital requirements, with the Hermit model having the lowest of them all. So it looks like models with fewer parameters have lower misestimation risk or lower misestimation capital requirements. However, overly simple laws or overly rigid laws, like the Gompertz one, don't fit quite well enough to be justifiable. So to conclude, we have a concept of misestimation risk, which stems from having a limited quantity of experience data. And when we're quantifying our misestimation risk, it needs to be statistical to get proper standard errors for our estimates, to account for correlations between parameters. And it has to be quantified financially to account for our concentration risk. We've got 2 alternative views of misestimation risk. We have the runoff approach, which would be useful for pricing block transactions like longevity swaps, bulk annuities, reinsurance treaties, any large transaction involving a large number of policies or lives. And then we have this value at risk approach to misestimation, which would be suitable for Solvency II reporting and ORSA work. And for the 1-year misestimation approach, the value at risk misestimation approach, we've seen that parameter risk is a surprisingly minor driver of the 1-year capital requirements. And instead, most of the capital requirements are in fact driven by what's called recalibration risk. And in fact, there's a very strong correlation between, or as a result of this recalibration risk dominating, there's a very strong correlation between 1-year misestimation VAR capital and idiosyncratic risk. To conclude, thanks to Gavin, Patrick, and Andrew for some of the helpful comments on some earlier drafts of this presentation. Copies available on our website. We've got some references here if anyone wants to go and do some more reading. A copy of the paper on which this presentation is based is available on the profession's website. So I think at this stage, it's maybe question time.
Yeah, thank you, Stephen. It's a really interesting presentation, and we've had a few questions coming in, so I'll feed those through. So kickoff question was, so for the first approach you presented, the runoff approach, there are two ways you look at modeling it. So you've got the delta approach and the sampling approach, whereas for the VAR approach, we're only looking at the sampling. Is there a way we could adapt the delta approach to be used on the VAR methodology?
No, not that I can think of. The difference lies in this recalibration aspect, the simulation of experience and the recalibration. I've yet to think of a way whereby you could do a value at risk approach and take advantage of, say, the delta method for that. I think this is fundamentally, the VAR approach is a recalibration approach to looking at risk. And I can't think of a way to exploit the delta method. I think you just have to do this through simulation and recalibration, unfortunately.
Great, thank you. I had a question in from Sarah O'Sullivan. So we said earlier that the parameter distribution was a Poisson, but yet close enough to the normal maximum likelihood distribution. So first part of the question is how do we assess that it was a Poisson distribution? And subsequently, how would any of the results change if we actually used that real distribution rather than assuming that it was a normal? So can we just substitute in a Poisson?
Right. That unfortunately is based on a misapprehension. There's no Poisson assumption anywhere in this methodology. All I did was, in order to illustrate the shape of a likelihood function, I happened to pick a Poisson variable, a Poisson random variable. So one of the earlier slides, to show the one-dimensional likelihood shapes, I picked a Poisson distribution. But that distribution assumption is nowhere else in the presentation. It was purely for illustrating the shape of a likelihood in one dimension.
Thank you for clarifying.
I can see there's another question. Why are you doing the refitting of the parameter at all in the VAR approach? Are you not fitting a parameter to your already known uncertainty in the parameter? Okay. The reason I'm doing the refitting is because it's answering the value at risk question. The value at risk question is, by how much could my liabilities change in the following year from new knowledge, from additional years experience? And in order to do that, I need to fit the model to the experience or the new experience in that year. So it's unavoidable that the value at risk approach involves the refitting of the model, because that's in essence, that's what the VAR question is by how much can my liabilities change from refitting the model. A question here from Andrew on slide 78. Is the simulation here including a stochastic period effect? I'll go to slide 78 to illustrate. Right. There is not a stochastic period effect at all. So it's not that which is driving the recalibration risk. What I've done is the simulation of the next year's experience is based purely on the parameters in the model, which is basically just the age and gender and pension size and the other differentials. You would include a stochastic period effect if you were calculating, say, an adverse experience effect. So that might be done separately. So what we've got here is that the idiosyncratic risk is assuming, if you like, perfect knowledge of the mortality differentials, and it doesn't include any additional period effect, which would obviously drive more idiosyncratic risk. So no, there's no stochastic period effect driving this recalibration risk. So yes, it's these results are purely based on the recalibration.
One more question I had, Stephen. So I guess the VAR calculation stuff we've shown here is based on a relatively modest sized book of lives. If we had a much larger block of lives, like a sort of a large insurance company might have, you got any intuition as to how the results would look, particularly with the parameter part and the recalibration part?
Yes, this is actually covered in the paper. There are some sections in the paper which I haven't actually covered in the presentation, and there's a specific section on the impact of portfolio size. So what I did was I took the portfolio and I just duplicated it 10 times to make the portfolio 10 times bigger and closer to what a large insurer would have. But it was obviously the same experience with the same risk factors, and when you fit the model, you get the same parameter estimates, but with a much smaller standard error on the parameters. And in the paper, you can actually see that there's considerably lower misestimation capital requirements for a larger portfolio. So I don't have it to hand to put it on screen, but if you look at the paper, there's a section with a graph showing how much lower the capital requirements are for larger portfolio sizes.
Excellent, thank you. No, that makes sense.
I think there's another there's another question here. This is a good one. The 1-year VAR horizon. Don't you think it's deeply stupid, given that policyholders' reasonable expectations are that the company will pay their claims when they fall due, which may be many years hence? That's an interesting question, because annuity business is essentially the risks are largely in runoff. It's very unlikely that an annuity portfolio will be unable to pay policyholders over a 1 or even a 10-year time horizon. So arguably longevity risk and annuity business in general is a poor fit for the value at risk regime, because most of the risks are long-term runoff risks. In contrast to, say, term assurance, where a pandemic, for example, would potentially drive a large spike in claims, which could in fact lead to the inability to pay. So annuity business is an example of a class of insurance business that is not a great fit for this 1-year value at risk approach, but that is the way the regulations are framed. Therefore, that is the way that we need to do our calculations and calculate our capital and present our results. Andrew says the simulation approach assumes multivariate normality. True. Suppose you do n simulation scenarios under this assumption and then calculate for each simulated theta. Could you calculate the true likelihood for each simulated theta and compare this to the multivariate likelihood? Yes, you can. I do this in the paper. I look at the shape of the profile likelihood. So it's the shape of the log likelihood function for each particular parameter. And it's an important assumption because these profile likelihoods need to be quadratic for the multivariate normal assumption to be valid. This is actually worth checking when you're fitting the model and carrying out these calculations. I think the rest of Andrew's question is rather long, and I probably need time to read it all. Yeah, I think the central point, Andrew's central point is the quadratic approximation might be very good around the parameter estimate, but it might be less good as we get further away from the center. So it's worth maybe going to the earlier example to show this. I think the question that Andrew is getting at, let's go back and find it. There we go. So the point, and Andrew's point, is the solid line, solid black line is the real likelihood function, and the dashed line is the quadratic approximation that is inherent in a normal likelihood. Now, as long as we are dealing in a range, say, plus or minus 95% confidence interval, there's next to no difference between the quadratic shape and the log likelihood function's actual shape. But as you get further and further away from the estimate, the closeness of the approximation becomes poorer. I think Andrew's point is that if you're looking at really extreme parameter deviations, then the quadratic approximation behind the multivariate normal assumption might be less good. Now, visually here, we can see that, in fact, as you go very far away from the parameter estimate, that is, in fact, the case. As a rough guide, you could say that 2 log likelihood units down from the peak is equivalent to a 95% confidence interval. So that might be, let's say, round about here where the hand is. Hopefully you can see that. So it's still fairly close. I don't think it would necessarily be a real cause for concern. If it were cause for concern, say, for example, that the log likelihood function, the profile likelihoods didn't have a properly quadratic shape, then you might need to exercise a little bit of actuarial judgment and maybe just do some rounding up of your capital requirements to reflect the fact that the multivariate normal distribution is an approximation, is not perfect. Sarah actually seems to be asking the same question as Andrew. What if the parameter distribution is not multivariate normal in reality? If that were the case, then I think you'd need to refit your model. It does happen with some parameters that you don't get a quadratic shape, and there's an example in the paper where one of the parameters and one of the Macon parameters does not have the proper quadratic shape. So as you can see from that table in the paper, although that one parameter doesn't have a proper quadratic shape, it doesn't seem to have had any material impact on the misestimation assessment. It doesn't look as though it's produced invalid results, because they are in fact consistent. The capital requirements are consistent with the results from other models where the quadratic shape is justified. I think we seem to have the number of questions seems to have stopped. Any more?
No, I think you must have covered it all off well, Stephen. So all that remains is for me to thank you for the presentation this morning, and on behalf of the audience, yeah, that's been really, really informative. Thank you. There will be a survey, like a questionnaire, being emailed out to participants, so we'd welcome any feedback on the presentation or the approach. So that's be coming out to your inboxes shortly. So yeah, thank you for Stephen. That's all for today.